Hello and welcome to Lab 2, Gravity and Drag. I'm Carson Lawler and this is my lab presentation. So, first we have the observed values, which were calculated using Tracker, the auto tracker, but unfortunately, due to the blur of the falling object and my camera's quality, I had to select manually many of the frames, which could cause some of the variation that is seen in the model. Next we have the computed values, which were all done in GlowScript, VPython, which everyone knows what it is already. Anyway, here's the position and velocity. Here's just a snippet of the code. Now, some things to consider is that for the code, as a lot of what I said, it's all smooth. And the reason that it's flat over here is because that's just to account for the time when I did not drop it and was just holding it during the video. Oh yeah, one thing to mention is that the velocity, the position is all calculated by using the velocity. Here's the difference between the two. As you can see, well, if I hold the laptop right, as you can see, the two match fairly closely, but there's a lot more irregularities with the actual observed one compared to the smoothness of the computed version. Yes, so in comparison, they are very similar. There's obviously much more roughness in the real version. Can you see that? Okay. Now the computer model takes out a lot of the complexity that the real version actually has, which not just drag, but a lot of other very hard to measure factors. Now, here's something to consider is that if instead of dropping the ball, I'd actually thrown it straight down. And in the long run, this would not have changed very much. It would have reached the terminal velocity faster, but the final terminal velocity, would still be the same in the end. Now, here's just a model showing how that would look. You can see right here is if I had thrown the ball straight down and just added a lot of negative velocity. And the position, and then the velocity of just the regular one. Now, what does this all mean? It means that drag is the only way to really calculate a terminal velocity for falling objects, because without it, a falling object would simply continue accelerating due to the force of gravity forever, or until it hits the ground. The drag adds terminal velocity to the mix, which reduces the at final velocity. It reduces the force of gravity to 0 once the velocity is high enough. Here are two graphs, and as you can see, these are position graphs. As you see, the position, or the slope of the position graph with drag, eventually starts to flatten out, compared to here where it follows the standard x squared curve. All right, thank you. I hope you have a great day.